This is Spacetime, Series 24, Episode 34. Coming up on Spacetime, amazing new images reveal magnetic structures near a supermassive black hole, a cosmic jellyfish in the distant universe, and stunning new results challenge the standard model of particle physics. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
The Event Horizon Telescope collaboration, which produced the first ever image of a black hole, has now released a new image detailing the powerful magnetic fields generated by the supermassive black hole. This new view examines the supermassive black hole at the centre of Messier 87 through polarized light. It's the first time astronomers have been able to measure polarization, a signature of magnetic fields, this close to the edge of a black hole. The observations are key to explaining how the Messier 87 galaxy, located some 55 million light-years away, is able to launch such energetic jets from its core. In fact, this is the next crucial piece of evidence needed to understand how magnetic fields behave around black holes, and how activity in this very compact region of space can drive these powerful jets that extend far beyond the galaxy. Back on April the 10th, 2019, the world was astonished when scientists released the first ever direct image of a black hole, revealing a bright ring-like structure with a central dark region, the black hole shadow. Now, since then, the Event Horizon Telescope collaboration has been delving deeper into the data on that supermassive object at the heart of M87, originally collected back in 2017. And they've discovered that a significant fraction of the light around the M87 black hole is polarized. And that's important because the polarization of light carries information that allows astronomers to better understand the physics behind the image. Light becomes polarized when it goes through certain filters, like the lenses of polarized sunglasses, or when it's emitted in a hot region of space where magnetic fields are present. In the same way that polarized sunglasses help you see better by reducing reflections and the glare from bright surfaces, astronomers can sharpen their view of the region around a black hole by looking at how the light originating from it is being polarized. Specifically, polarization allows astronomers to map the magnetic field lines present near the inner edge of the black hole, right near that boundary between the accretion disk and the black hole itself. And these new polarized images are key to understanding how the magnetic field allows the black hole to consume matter and generate these powerful jets. The bright jets of energy and matter that emerge from M87's core and extend out at least 5,000 light-years from its center are one of the galaxy's most mysterious and energetic features. It works like this. Most of the material lying close to the inner edge of a black hole's accretion disk will eventually pass a point of no return, called the event horizon. And once it passes beyond that event horizon, the material falls forever into the black hole's singularity. Now, no one can tell you exactly what a singularity is. It's best defined as a point of infinite density and zero volume, where science's understanding of the laws of physics falls apart. However, some of the surrounding particles on the accretion disk manage to escape moments before reaching the event horizon, and it's those particles which are blown into space and form the jets. Astronomers have relied on a range of different models of how matter behaves near a black hole to try and better understand this process. But to be honest, they really don't know exactly how jets larger than the galaxy are launched from its central region, which is comparable in size to our solar system, nor exactly how matter falls into the black hole. But with this new Event Horizon Telescope image of the black hole and its shadow in polarized light, astronomers have managed to peer into the region just outside the black hole, where this interplay between matter flowing beyond the event horizon and matter being ejected out is happening. The observations are providing new information about the structure of the magnetic fields just outside the black hole. And the team found that theoretical models featuring highly magnetized plasma can best explain what they're seeing at the event horizon. The observations are suggesting that the magnetic fields of the black hole's edge are strong enough to push back on the hot gas, helping it to resist the pull of gravity. And so only gas that slips through this magnetic field can spiral inwards to the event horizon. This is Space-Time. Still to come, a cosmic jellyfish in the distant universe, and new results challenging the standard model of particle physics. All that and more still to come on Space-Time. Astronomers have discovered a spectacular cloud of plasma being ignited by passing shock waves in a distant cluster of galaxies. The findings, reported in the Astrophysical Journal, were captured by scientists using the Murchison Wide Field Array radio telescope in outback Western Australia. One of the study's authors, Professor Melanie Johnston-Hollett from the Curtin University node of the International Centre for Radio Astronomy Research, says the massive plasma cloud, which bears a striking resemblance to a giant cosmic jellyfish, was detected in a distant galaxy cluster known as Abell 2877. The authors observed the cluster for 12 hours at 5 radio frequencies between 87.5 and 215.5 MHz. As they studied the feature, a ghostly, jellyfish-like structure began to emerge at lower and lower frequencies. Yet, strangely enough, when they look back at higher frequencies, the emission all but disappears. The author's best explanation for the phenomenon is that some 2 billion years ago, a handful of supermassive black holes from multiple galaxies in the cluster spewed out powerful jets of plasma, similar to the ones we were talking about in our previous story. Now, over the eons, this plasma gradually faded and went quiet. It lay dormant. Then, quite recently, the plasma from these events began mixing, and at the same time, gentle shock waves passed through the system, briefly reigniting the plasma, lighting up the jellyfish and its tentacles. Now, as seen from Earth, the cosmic jellyfish is enormous, covering an area of the sky a third the diameter of the Moon. But it's really only visible using the unique capabilities of the Murchison Wide Field Array. This array is one of the precursors for the multi-billion-dollar Square Kilometre Array project, which will build the world's largest radio telescope, and which will have thousands of times more sensitivity with much higher resolution. Johnston-Hollett says discoveries like the cosmic jellyfish hint at what's still to come once the Square Kilometre Array becomes operational.
So Abell 2877 itself is not a very interesting galaxy cluster, which is a grouping of several hundred galaxies sitting in a gravitational potential well, but it hosts in it a very strange object that we've just seen at low radio frequencies with the Murchison Wide Field Array, the so-called space jellyfish, which is an enormous region of space shaped like a jellyfish, which is emitting only at very low radio frequencies and can only be picked up by telescopes like the MWA. And we've never seen anything which has the characteristics of this space jellyfish before. So the particular part that's interesting for us as radio astronomers is that it's only visible below 200 megahertz, so very, very low radio frequencies, and we can't see it at all. And the emission drops off really, really fast as a function of frequency, which tells us something about the electrons that are causing that radio emission. And it's not anything that we've seen before, so it's kind of cool.
This is what, a giant blob of plasma just sitting there?
Yeah, pretty much. So it's a bunch of electrons that have been very gently accelerated or re-accelerated, sitting in the edges of the galaxy cluster. So what we think's happened is that about 2 billion years ago, there was a couple of AGNs, so active galactic nuclei, which hosted supermassive black holes, that have leaked out a whole bunch of electrons into the intracluster medium, and then cluster-wide processes that are not as violent as the ones we typically see when we've got two galaxy clusters merging have caused those electrons to re-accelerate, and then they light up in the radio. But they don't light up very much. They're very dim. So, in fact, they're so dim that, as I said, we don't see them except at very, very low radio frequencies because they're only really producing very low energy radio photons. So it's really interesting. It's a thing that we've never seen before, didn't really expect, and yeah, it looks like a jellyfish in space. It's super cool.
What's it telling us about that part of space?
So we've termed this a polyphenix. So we have this idea of electrons that leak out of supermassive black holes. They emit radio waves until they run out of energy, and then they just sort of sit there. Something will go through and provide them with some more energy, so either turbulence in the galaxy cluster or a shockwave or something like this, and they light up again and produce more radio emission. Now, we see these quite a lot, and we see them usually from one particular AGN, so we call this a phoenix, sort of the rising from the dead kind of thing. This one's interesting because it's more than one active galactic nuclei with the supermassive black hole that has produced the electron population. It's over the entire volume of the galaxy cluster, so they've been leaking electrons out for a long time, and yet the processes that are causing them to light back up are very, very low energy, gentle processes in the galaxy cluster. So what it tells us is that this type of source is probably more prevalent in the universe, and we've just not seen them before. And it's only really the advent of these fantastic low-frequency radio telescopes that we've got, like the Murchison Wide Field Array, that have allowed us to detect this type of thing.
I take it you'll be looking for more of them?
Oh, absolutely. Well, hopefully. So we're doing sky survey again with the MWA. So we did a very successful sky survey a few years ago with the phase 1 of the Murchison Wide Field Array. So we've looked at about 3/4 of the sky at low frequencies, but we've since gone ahead and upgraded the telescope. So we've doubled the number of antennae and increased the sensitivity by a factor of about 10, and we're resurveying the sky and reprocessing it. So hopefully we'll be able to find more of these things. They should be out there lurking in the depths of space, so to speak.
That's Professor Melanie Johnston-Hollett from the Curtin University node of the International Centre for Radio Astronomy Research. And this is Space Time. Still to come, intriguing new results from CERN challenging the standard model of particle physics. And Rocket Lab launches a revolutionary new Australian satellite, or is it 2 satellites? All that and more still to come on Space Time. Scientists at CERN have found some intriguing new results that potentially can't be explained by science's current understanding of the laws of physics. Researchers with the L8CB collaboration at the Large Hadron Collider, the world's largest atom smasher, have detected particles not behaving the way they should according to the standard model of particle physics, the basic foundation for science's understanding of the universe. The standard model predicts that a type of subatomic particle known as a bottom or beauty quark, which measured by the L8CB experiment, should decay into either muons or electrons in roughly equal amounts. However, the new results suggest this isn't happening, and that therefore could be pointing to the existence of new particles or interactions not explained by the standard model. The standard model is the current best theory of particle physics, describing all the known fundamental particles that make up the universe and the forces they interact with. However, it's by no means complete. The standard model can't explain some of the deepest mysteries in modern physics. Things like what dark matter is, what dark energy is, and why there's an imbalance between matter and antimatter in the universe. After all, equal amounts of matter and antimatter were made when the universe formed 13.8 billion years ago, and matter and antimatter annihilate when they come into contact with each other. Yet that clearly didn't happen because we're here, and we're in a universe made primarily of matter, not antimatter. So there's a lot of questions to answer. To try and help explain some of these mysteries, scientists have been searching for particles acting in ways that are different from what's predicted by the standard model. And that's exactly what they may have found. One of the study's authors, Dr. Mitesh Patel from Imperial College London, says he started shaking when he first looked at the results. Now, while it's still far too early to determine if it really does represent a deviation from the standard model, the potential implications are stunning. The results were produced by the L8CB experiment, one of 4 huge particle detectors on the Large Hadron Collider, a giant 27-kilometre-long underground ring located near Geneva on the Franco-Swiss border. Scientists accelerate subatomic particles at 99.999% the speed of light in opposite directions along the ring. These now subluminal particle packets collide when they reach one of the 4 detectors. These collisions produce the sort of environment, temperatures and pressures that existed in the first milliseconds after the Big Bang, in the process generating a burst of new particles which physicists then record and study in order to better understand the basic building blocks of nature. And what the L8CB team have found is that their measurements question the laws of physics that treat electrons and their heavier counterparts muons identically, except for small differences due to their different masses. You see, according to the Standard Model, muons and electrons interact with all the forces of nature in the same way. So beauty quarks created at the L8CB should decay into muons just as often as they do into electrons. But the new measurements suggest the decays are happening at different rates. And that in turn could suggest never-before-seen particles tipping the scales away from muons. This new result, therefore, offers tantalizing hints of the presence of a new fundamental particle or force that interacts differently with the different types of particles. And it doesn't end there, because this new data simply represents the most significant finding in a whole series of L8CB results over the past decade that all seem to be lining up exactly the same way. And it's that which all seems to be pointing to a common explanation. And because the results aren't changing, it means their uncertainties are shrinking, and that's increasing science's ability to see possible differences with the Standard Model. In particle physics, the gold standard for a discovery is 5 sigma, or 5 standard deviations. Now, in practical terms, what that means is a 1 in 3.5 million chance of the result you have being simply a fluke. 1 in 3.5 million. This result isn't quite that good. It's 3 deviations. But that's still a 1 in 1,000 chance that these measurements are simply a statistical coincidence. 1 in 1,000. So, by particle physics standards, it's still far too soon to make any firm conclusions as to whether or not there could be something wrong with science's current understanding of particle physics. It's now up to the L8CB collaboration to further verify their results by collating and analysing more data to see if the evidence for some new phenomenon remains or whether it disappears as more and more results come in. And the L8CB experiment's expected to start collecting new data next year following an upgrade to the detector. This is Space Time. Still to come, Rocket Lab launches a revolutionary new Australian satellite. Or is it 2 satellites? And later in the science report, the Oxford AstraZeneca vaccine found to be ineffective against the South African strain of COVID-19. All that and more still to come on Space Time. Rocket Lab has successfully launched its 19th Electron mission, aboard which was its 100th satellite payload. The flight included the revolutionary M2 experimental satellite, built by the University of New South Wales in collaboration with the Royal Australian Air Force. It's testing emerging technologies in Earth observation, maritime surveillance and satellite communication capabilities using advanced in-orbit artificial intelligence on a platform that's reconfigurable throughout the mission. The data being captured by M2 can inform maritime surveillance, weather observations, and low-orbit satellite traffic space situational awareness. M2 can also be split into 2 independent spacecraft, which can then fly in formation to enhance mission flexibility. Also aboard the 19th Electron mission were 2 Internet of Things nanosatellites for the Australian commercial operator Fleet Space, a technology demonstrator for the US Army Space and Missile Defense Command, a weather monitoring CubeSat for Care Weather Technologies, and an Earth observation satellite for Black Sky Global. The mission, named They Go Up So Fast, took off from Rocket Lab's Mahia Peninsula Launch Complex 1 on New Zealand's North Island east coast.
AFTS is green and enabled for flight.
At this time, I can confirm LD is go for launch.
UVs are on internal power.
LOX load is complete. System is in recirculation.
Stage 1 and Stage 2 are pressed for flight.
Water deluge is activated.
10, 9, 8, 7, 6, 5, 4, 3, 2...
They really do go up so fast with a beautiful liftoff of Electron from the pad at Launch Complex 1. We're now T plus 40 seconds into the mission and approaching max Q, or maximum aerodynamic pressure, at the 1 minute 9 mark. Max Q is the moment during launch when Electron experiences the highest amount of mechanical stress from the dynamic pressure, which is a function of its velocity and altitude.
Vehicle past maximum dynamic pressure. Stage 1 guidance is nominal.
AOS Chatham Station.
We're quickly approaching the next set of milestones in this mission. First up will be main engine cutoff of the 9 Rutherford engines on Electron's first stage. This is when the engines throttle down before the vehicle separates into sections, or what we call stages. Following that, the sole vacuum-optimized Rutherford engine on that second stage will fire up to continue the journey to low Earth orbit.
Stage separation successful.
Stage 2 ignition confirmed.
We have had a successful MECO, first and second stage separation and ignition of the Rutherford engine on Electron's second stage. Coming up in a few seconds, Electron's fairing will separate. The fairing is the casing at the top of the rocket that protects the satellites as they travel through Earth's atmosphere.
Fairing jettison succeeded.
And there they go, the fairing has cleanly separated and fallen away from Electron, which is continuing on a nominal trajectory.
Current speed of just under 10,000 kilometers per hour and an altitude of about 165 kilometers, and we are now at about 4 minutes into the mission.
Starting throttle down on stage 2.
Stage 2 propulsion remains nominal.
High voltage battery discharge nominal. Approaching hot swap.
In the next few moments, we'll be coming up to the battery hot swap, a maneuver that's very specific to the Electron rocket as the only launch vehicle flying with battery-powered electric pumps feeding our engines. When the first set of batteries are depleted during launch, we switch to a fresh one to power the engine for the rest of the mission.
Battery jettison confirmed.
Propulsion remains nominal.
And there we go, that's confirmation that the battery hot swap was performed successfully on Electron, and propulsion continues to look good for the rocket's second stage Rutherford engine. We're just a few minutes away from orbital insertion and kick stage separation on this mission.
Current altitude is 280 kilometers, speed 4.9 kilometers per second.
The Electron rocket's kick stage deployed 5 of the satellites into individual 550-kilometre high orbits before reigniting its Curie engine and then lowering its orbit by 100 kilometres to deploy the final payload. The kick stage then reconfigured itself into Rocket Lab's new Photon spacecraft, which is equipped with new power management, thermal control and attitude control subsystems that will be utilised for NASA's capstone mission to the Moon later this year. The so-called Photon Pathstone mission is also testing new on-orbit deep space radio capabilities, an upgraded reaction control system for space maneuverability, and both sun sensors and star trackers for situational awareness and navigation. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. As Australian-produced Oxford AstraZeneca vaccines begin widespread distribution, comes news from a long-anticipated United States trial that the vaccine is 79% effective at preventing symptomatic cases of COVID-19, including in older adults. The FDA study involving 30,000 participants is consistent with British trial results. It shows no severe illnesses or hospitalizations among vaccinated volunteers, including no increased risks of rare blood clots like those identified in Europe, a scare that led to numerous countries briefly suspending vaccinations earlier this month. But there are common side effects, including headache, muscle pain, chills, fever, tiredness, and feeling generally unwell. But all that usually only lasts a day or so and then disappears like it never happened. And many people who have received the Pfizer vaccine instead have reported the same side effects, even though the two vaccines work differently. Australia currently plans on producing more than 500,000 doses of the AstraZeneca vaccine every week. However, the news isn't all good. New tests published in the New England Journal of Medicine show that the Oxford AstraZeneca COVID-19 vaccine is ineffective against the South African B.1.351 variant of the virus. Scientists tested the vaccine on around 2,000 people, roughly half of whom received the 2-dose jab, while the rest were given a placebo. 19 out of the 750 vaccine recipients caught mild to moderate COVID-19 following the jabs, while 23 out of the 717 placebo recipients caught it, suggesting an efficacy of just 21.9%. But not all of those people had the South African variant. And when the two groups of patients were analysed alone, the vaccine's efficacy was even lower, just 10.4%. AstraZeneca will shortly begin trials on a new next-generation vaccine that should work against all current SARS-CoV-2 variants, including the South African strain, which could be available before the end of the year. So I guess we'll all be going back for a booster next year. Meanwhile, scientists at Israel's Ben Gurion University have found the Pfizer vaccine to be moderately less effective against the South African variant, although still successful against both the British strain and the original SARS-CoV-2 Chinese Wuhan strain. Their findings are reported in the journal Cell Host and Microbe. Over 2.8 million people have now died from the COVID-19 coronavirus, with another 151 million infected since the deadly disease first emerged from the Wuhan Virology Lab in China and spread around the world. A new study warns against letting little kids spend too much time on computers and smartphones. A report in the British Medical Journal claims overuse of mobile phones, tablets and game consoles at an early age is linked to a higher risk of behavioural problems by the age of 5. These include being hyperactive, having a short attention span, having low concentration levels, and experiencing friendship problems. The data is based on a study from Finland, which suggests that 95% of children exceeded the 1 hour recommended daily device use. Meanwhile, Finnish authorities have traced a cyber attack against the country's parliament last year to a Chinese government hacker group. Last December, the Finnish parliament announced that it had been hacked. Finland's SUPO security service worked with US security firm FireEye to track down and identify the source of the hack, eventually tracing it to China's APT31 hacking group. According to FireEye, APT31 focuses on obtaining information that can provide the Chinese government and state-owned enterprises with political, economic and military advantages. Well, if you're looking for an excuse to sneak in a quick afternoon siesta, you'll be interested in a new study which has found that taking a regular afternoon nap may be linked to improved mental agility. Scientists examined 2,214 people, 1,534 of whom enjoyed a regular afternoon snooze. Their findings, reported in the journal General Psychiatry, suggest that a quick kip in the afternoon was associated with better locational awareness, verbal fluency, and working memory. Although this type of study can't show that napping actually caused the differences in mental performance, the authors say sleep may help ward off inflammation in the body, which could help explain the brain boost for those who choose to doze. A new study has found people are becoming more hesitant about getting the COVID-19 vaccine. The findings are based on a survey by the Australian National University, which suggests a significant and substantial increase in vaccine hesitancy over the past 6 months. The people asked about their feelings on getting the vaccine are becoming less willing, increasing by 31.9% between August 2020 and January 2021. Tim Mendham from Australian Skeptics says the study found females, Indigenous Australians, those who speak a language other than English at home, and those who have not completed Year 12 have all become less willing to get the vaccine compared to the rest of the Australian population.
Various surveys have been done, obviously around the world too, but there's various surveys been done in Australia to indicate that there's a lot of people out there who say they won't, probably or definitely will not take the vaccination. Now, this one particular survey said 20% say they're unlikely to. Other surveys, Department of Health said there's 27% are unsure. So you're talking about a fair percentage of the population. But I did my numbers on the back of an envelope, so you can correct me if I'm wrong. But these same surveys said about 64, 65, 70% of people say they will definitely get it. And we assume that a lot of the people who are hesitant are probably primarily hesitant because of the speed at which this vaccine has been produced and is being used around the world, especially when politicians say that, vaccine production normally takes 5 to 10 years. This one's been done in 1 year, and you think, well, hang on, why? So that's scared a lot of people, and that's what makes them hesitant. But once they see what's happening in the world, and once they see how vaccines are working, effective, and they are apparently, a lot of those percentage, let's say half of it even, will say, yeah, okay, I'll get it, because I'm just hesitant. It doesn't mean I'm not going to get it. And so you add that to the people who are immunocompromised, who cannot take a vaccine because of their physical issues, allergies and things like that, and that's a genuine thing that happens. You add it up and you're actually getting over 90% of people perhaps 85, 90, 85 on a conservative sort of estimate, if you like. And then you get the people who are the lazy parent contingency, who are the ones that say, I'm doing something that day, I've got to get my fingernails polished. And if everyone else gets it, that's okay, we're safe. Now, some of those will turn into getting vaccination, especially thanks to no jab, no pay, and no jab, no play legislation. So those people are getting less lazy, so they're moving across. The surveys say at about 9%, whatever, of people are anti-vax, so they're absolutely saying we will not vaccinate. And I think this is part of the scare tactics that we're seeing at the moment, which is pretty strong. And normally the anti-vax numbers is about 4 to 5%. So if you take the anti-vax people and throw in 1% or 2% for the lazy parent people, you're down to about 95% of people will get the vaccination. 95% is herd immunity. That allows for the fact that there are people out there who can't get a vaccination need to be protected by the rest of us being vaccinated. So 90% in Australia, in most places it's above 90%. I think Victoria reached 95. I don't know if it's still there. It goes up and down depending on, by 1% or 2%. The worst case are people where there's sort of, hippie country like Byron Bay, Mullumbimby, Nimbin, those sort of areas where it's 50%, 60%, and that's where you're getting these diseases returning, whooping cough and things like that. But to me, this is a scary survey. It's saying 20%, but me being the eternal optimist, I pull back and look at that. What does that 20% mean? And most of those are hesitant, not anti. They say you probably won't get it, but it also means you probably will eventually, right? Once the whole hysteria settles down because of the effectiveness of being proved.
A lot of the concern has been regarding the speed at which these vaccines are being produced. But what people need to understand is the vaccine framework, the scaffolding upon which these vaccines are based, has been around for quite a while now. And all they're really doing is changing a few of the chemical compounds involved in the final stages of these in order to make the protein spikes that they're trying to make or to encourage the human body to make, depending on which version of the vaccine you're getting. So although it is happening really quickly, it's all based on a very firm foundation.
That's right. I mean, there have been various coronaviruses of various sorts around for a while. I mean, a corona just indicating it's the shape of the virus rather than its nature. Add to that, the crown. Add to that the number of organisations and the effort being put in, which is above and beyond what's been done before. And yes, sort of 1 year becomes understandable. The question then comes down to how diligent have the trials been in that short period of time.
And that's a legitimate question. We saw with the Oxford AstraZeneca vaccine, there have been some compromises in the trials associated with that, but hopefully they've now been sorted out with the latest trials that have just come through.
That's right. I mean, trials are part and parcel of the number of years it takes to develop a vaccine. But as you say, if they're building on top of past research, some of that research time can be dismissed, and you're really down to the trial stage. When the trials are time you can't shorten, really, unless you're doing a hell of a lot of them very quickly. But, I mean, it's still, the fact that politicians say normally it takes 5-10 years, this one's only taking 1, has scared a lot of people. And that's a fact, but it's a fact that people will get over, I think.
That's Tim Mendham from Australian Skeptics. And that's the show for now. Spacetime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. Spacetime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the Spacetime store for a range of promotional merchandising goodies, or by becoming a Spacetime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to facebook.com/Spacetime with Stuart Gary. And Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.